Now we want to compute h1 of k. So let's start again just like before. For any small c belongs to c1 of k, we have L1 c. This is the small c. L1 a p0 p1 b p1 p2 c p2 p0. Then we have c minus a p0 a minus b p1 b minus c p2, and all my a, b, and c belongs to the group of integers. And the quantity I wrote down, let's say this is equation number 2. To find the cycle group, we need to make this guy 0. So if I impose the condition this, then this implies c minus a p0 a minus b p1 b minus c p2 will be 0, and this condition is only satisfied when a equals to c equals to b. This is easily seen, right? So any element on the cycle group capital Z can be written as follows. So for any small z belongs to capital Z, 1 of k can be written as p0 p1. Okay, let's not use the first braces, since we use first braces to denote the orientation of the simplest. Let's use a third brace. Okay, let's not confuse ourselves. p0 p1, it will be p1 p2, and we have a p2 p0 like this. Okay, that's good. We have some idea about our cycle group and the chain group. Now the final element of the recipe, that is the boundary group. To find b1, we do the following. To find b1, we need to have a 2 simplex, right? Oh, I'm sorry, I think I missed a 2 simplex earlier. How did, yeah, there should be another element, because this actually this thing is supposed to give me a triangle, a solid field in triangle, so it should contain a p0 p1 p2. Sorry about that. However, it doesn't affect the calculation of h0 of k, and you can easily understand why, because you are starting with a c0 thing, right? You are starting with a 0 chain complex, then you are moving on. So it contains another element, p0 p1 and p2, and yeah, you are computing the homology groups of a triangle, solid field in triangle. Where should I put it? Yeah. Okay. Now, to find b1 of k, we need to have any element that is a 2 simplex, and any 2 simplex can be written, let's say, some d and p0 p1 p2, where d belongs to z, right? So we want to find elements of b1, so this will satisfy d p0 p1 p2 like this, and if you apply the boundary operator on it and do the computation, you'll have the result, which is fairly easy to see, p0 p1 with p1 p2, then you have a p2 p0 like this. And if we compare the elements of z1 and b1, we see that they are the same thing, right? Because this is an element of Z1 of k. This is an element of B1 of k. So it turns out computing the first homology group was way more easier than computing the zeroth homology group in this case. So the first homology group is just Z1 of k mod of B1 of k, and this is just isomorphic to the identity element. You may ask, okay, why? Well, these two groups are the same thing. So let's say my Z1 has some elements like this: alpha, beta, gamma, delta, right? And if you can recall, when we mod things out, B1, I have, let's say B1 contains alpha and delta, suppose. But in this case, since these two groups are the same, so I have to write all the elements, right? So all the elements are same: alpha, beta, gamma, delta. And when we quotient this, or we mod it, we interpret it as I take all the elements inside B1 and I shrunk them to identity. So all the elements are the same in these two cases. So all the elements will be shrunk to the identity, or so to say converted to the identity. And if the identity, let's say, is alpha, then I would write it as alpha, right? And for a group, identity is unique. So that's what's happening over here. We are dealing with group of integers, and when we have integers, the additive identity is just 0. So that's why I write it as a 0. And you can see that, or if you try to compute some h2, okay, let's not write h2, rather hn of k in this case, where n is equal or greater than 2, you can easily show that hn of k will always be 0. Now let's take a look at another example. This is example 3. Let the simplicial complex be is P0, P1, and P1 and P2. First we identify the chain groups. Now I'm writing it in a more organized manner so that you can understand easily. BP1, A comma B belongs to Z. C1 of K is just some C prime, or let's call them small c. P0, P1, like this, where small c belongs to Z. Okay. Let's compute H1K first. So computation of H1 of K. To do that, we need to work with C1K. We already have our C1K. We want to find what is the structure of Z1 of K. So let's say any small z belongs to Z1 of K. We want to find how these small z's look like. So these are the cycle groups, and they will satisfy the following. That is del 1 of z equals to 0, right? And now we need to find an explicit expression in terms of the simplexes for this set. And I want to write it as del 1 c p0 p1 equals to 0. You may ask why? Well, this is a one chain, right? And from a one chain we want to compute the one cycles. So that's how we do it. That's what we have been doing so far. So if I do that and I continue with this calculation, this will give me c p1 minus c times p0 equals to 0. And this is only possible if c equals to 0. Now we note that this P0 P1, the simplex, the one simplex P0 P1, it can't be the boundary of any simplex as well. Okay, and hence what we conclude is that the boundary set contains only the additive identity, or so to say 0 in this case. So since P0 P1 is, or so to say, can't be boundary of any simplex as well, hence B1 of k is 0, like this. So we have all the ingredients, and finally we want to compute h1 of k equals to z1 of k by b1 of k, which is just a 0. Because the reason I'm writing this as a 0, well, any element on z1, if you write it like some c p0 p1, and with you want to verify that whether they actually form a cycle from the chains, you understand that this is only possible, the condition that the boundary operator acting on the chains give us 0 is only possible when the coefficients itself are 0. So it's like the chain group is empty. You can think of it like that, or you can think of it like that it's just the identity, or a trivial. People always call it trivial, so you can also call it trivial. You can write it like this. You will already know that there's only the identity element in the boundary, so this is just the identity group, the trivial thing, or so to say 0 equivalently in terms of the numbers. Okay, and now let's compute h0 of k, and we'll again see the use of fundamental theorem of homomorphism over here. So our c0 of k was ap0 bp1, and we have our b0 of k. Again, I'm just talking about elements, okay? So these are just elements, so let me use this symbol. They consist of elements like this, that's what I mean. So I want to compute the b0s, and before I compute b0s, I want to compute our z0s as well. And you can easily see that the z0 of k will also assume this form. Why? Because take an element from the chain group, apply the boundary operator, it goes to 0, right? So that's why they're the same thing over here. So that's why since I showed that in the previous two examples, so that's why I'm not showing it on this one. And now we want to compute the elements, how the elements look like in the boundary set, or the 0 boundary. So this is del 1 c p0 p1 equals to c p1 minus p0. Now again, you have these things, but if you try to use the formula or the prescription, this one, it's not a straightforward computation. So again, we want to use the fundamental theorem of homomorphism, and you can see that we can just take the homomorphism that we defined in the earlier example again in this case as well. So let us define a homomorphism that maps z0 to the integers. Okay, and if I do that in such a way, it's acting on any element of z0. So how does the elements of z0 look like? It looks like this: a p0 b p1, right? And it will return this guy over here. So you can find the kernel of f inverse 0. Why this is the inverse 0? Well, the second group is G2. The identity over there is 0, right? So the inverse map of this f will produce the elements of the boundaries. So once you do that, you define this homomorphism, and we can easily see that this a plus b, which also belongs to z, is just the image of f. So we have h0 of k is z0 of k by b0 of k as the image of f. Why? Because we wrote it as, that means according to the fundamental theorem of homomorphism, this is just the kernel of f, right? Which is isomorphic to image of f. But image of f is just what? The group of integers. So your h0 of k is isomorphic to the set of integers. This is how we compute things in the homology group, and the idea is simple. First we start with the first we have to identify what type of homology group we want to compute. That is, whether we want to compute h0 or h1 or h2, whatever. Then we have to see that whether the chain complex for those things exist in my simplicial complex. And I start the general procedure is something like this, that we start with the chain complex. From there we find the cycles, and then we identify the boundaries, and then we use this formula or the fundamental theorem of homomorphism, whichever is convenient for us. Now, one thing you might have noticed is that in all these three examples, the zeroth homology group always came as the group of integers. Okay, so if you want to ask that, is there any sort of a pattern for this, or is there any sort of a reason?